Hello and welcome to week 4 in database systems. Jumping into our agenda, first we'll go over the assignments for this week, and then we'll talk about chapters 9 and then chapters 10. Moving into the assignments. For chapter 9, we're talking about the relational database design by ER and EER to relational mapping. Chapter 10, we talk about intro to SQL programming techniques. The first discussion, which centers on chapter 9, talks about database design. It's due by the end of this week, week 4, by midnight. And then the second discussion, chapter 10, talks about database programming. SQL programming is also due by the end of this week as well. So moving into the objectives for week 4, chapter 9 talks about the ER to relational mapping algorithm. We'll go through those 9 steps. Then chapter 10 talks about database program techniques, embedding SQL, dynamic SQL, and SQLJ, database programming with functional calls such as SQL/CLI and JDBC, and database stored procedures and SQL PSM, as well as the comparing those 3 approaches. Discussion 1 of this week centers on Chapter 9. Discuss the correspondences between the ER model constructs and the relational model constructs. Show how each ER model construct can be mapped to the relational model and discuss any alternative mappings. Do remember to do so in 250 to 300 words using appropriate citations. Make sure that you do reply to 2 of your classmates, and your first post should be made by Wednesday at midnight. Do engage and do build on the conversation. There must be at least 1 APA formatted reference in your initial post as well. Make sure that if you make claims in subsequent posts that you support them as well. In the second discussion of this 4th week it's about chapter 10. List the 3 main approaches to database programming. What are the advantages and disadvantages of each of those approaches? Again, 250 to 300 words. Make sure you do include a citation. Do respond to 2 of your classmates. Make sure your initial post is in by Wednesday at midnight. Moving on to chapter 9, which centers on relational database design by ER to EER to relational mapping. So section 9 deals with ER to relational mapping algorithm, and section 9.2 centers on mapping EER model constructs to relations. So the goals during mapping is to preserve all information that includes all attributes, maintain the constraints to the extent possible. Relational model cannot preserve all constraints. For example, max cardinality ratios such as 1 to 10 in ER, exhaustive classification into subtypes, etc. Students are specialized into domestic and foreign. Minimize null values. The mapping procedures described has been implemented in many commercial tools, and there are tools that do this stuff for you. You basically draw a diagram and they produce essentially the schema for you. The ER to relational mapping algorithm, and this is the first of 14. Step 1 is mapping of regular entity types. For each regular strong entity type E in the ER schema, create a relation R that includes all the simple attributes of E. Choose one of the key attributes of E as the primary key for R. If the chosen key of E is composite, the set of simple attributes that form it will together form the primary key of R. An example, we create the relations employee, department, and project in the relational schema corresponding to the regular entities in the ER diagram. SSN, DNUM, and PNUM are the primary keys for the relations employee, department, and project as shown. Figure 9.1 shows this relationship. Step 2, mapping of weak entity types. For each weak entity type W in the ER schema with owner entity type of E, create a relation R and include all simple attributes or simple components of composite attributes of W as attributes of R. Also include as foreign keys attributes of R the primary key attributes of the relation that correspond to the owner entity types. The primary key of R is the combination of the primary keys of the owner and the partial key of the weak entity type W, if any. An example, create the relation dependent in this step to correspond to the weak entity type dependent. Include the primary key SSN of the employee relation as the foreign key attribute of dependent, renamed as ESSN. The primary key of the dependent relation in the combination ESSN dependent name, because dependent name is the partial key of dependent. Step 3, mapping of binary one-to-one relation types. For each binary one-to-one relation type R in the ER schema, identify the relations S and T that correspond to the entity types participating in R. There are 3 possible approaches. One is foreign key, where 2 relations approach. Choose one of the relations, say S, and include a foreign key in the S, the primary key of T. It is better to choose an entity type with total participation in R in the role of S. An example is a one-to-one relation of manages is mapped by choosing the participating entity type department to serve in the role of S because it participates in the manages relationship type in total. The second step is to merge relation, that is, or the second alternative is to the merge relation, that is one relation option. An alternative mapping of a one-to-one relation type is possible by merging the 2 entity types and the relationship into a single relation. This may be appropriate when both participations are total. Cross-referencing is the third type, or relationship relation. This is 3 relations option. The third alternative is to set up a third relation R for the purpose of cross-referencing the primary keys of the 2 relations S and T representing the entity type. Step 4, mapping of binary 1-to-n relationship types. For each regular binary 1-to-n relationship type R, identify the relation S that represents the participating entity type at the inside of the relation type. Include as many as foreign keys in S, the primary key of the relation T that represents the other entity type participating in R. Include any simple attributes of the 1-to-n relation type as attributes of S. An example is a 1-to-n relationship over works for controls and supervision in the figure. For works for, we include the primary key D number of the department relation as a foreign key in the employee relation and call it DNO. An alternative approach is to use a relationship relation, a cross-referencing relation. This is rarely done, however. Step 5 involves mapping of binary M-to-N relation types. For each regular binary M of n relation type R, create a new relation S that represents R. This is a relationship relation. Include as foreign keys as foreign key attributes in S the primary keys of the relation that represent the participating entity type. This combination will form the primary key of S. Also include any simple attributes of the M-to-N relationship type or simple components of composite attributes as attributes of S. An example of an M-to-N relationship type is the works on from the ER diagram is mapped by creating a relation works on in the relational database schema. The primary keys of the project and employee relations are included as foreign keys in works on and renamed P&O and ESSN respectively. Attribute hours in works on represents the hours attribute of the relation type. The primary key of works on relation is the combination of the foreign key attributes. Step 6 is around mapping of multi-valued attributes. For each multi-valued attribute A, create a new relation R. This relation R will include an attribute corresponding to A plus the primary key attribute K as a foreign key in R of the relation that represents the entity type of relationship type that has A as an attribute. The primary key of R is the combination of A and K. If the multi-valued attribute is composite, we include its simple components. An example is the relation depart locations is created. The attribute D location represents the multi-valued attribute locations of departments, while D number as foreign key represents the primary key of the department relations. The primary key of R is the combination of D number and D location. Step 7 is the mapping of n-ary relation types. For each In-array relationship type R, where n is greater than 2, create a new relationship type S to represent R. Include as foreign key attributes in S the primary keys of the relations that represent the participating entity types. Also include any simple attributes of the in-array relationship type or simple components of composite attributes as attributes of S. An example is the relationship type supply SUPPY in the ER on the next slide. This can be mapped to the relation supply shown in the relational schema, whose primary key is the combination of the three foreign keys, S, name, part, num, and project num. A summary of the mapping constructs and constraints from the ER model to the relational model: entity type, entity relation, one-to-one or one-to-n relationship type is a foreign key or relationship. M to N is a relationship, relation, and two foreign keys. M to n-array relationship type is relationship, relation with n foreign keys. Simple attributes is an attribute. Composite attribute becomes a set of component attributes, and multi-valued attributes become relation and foreign keys. And value set becomes domain, and key attributes become primary or secondary keys. Moving on to chapter 10, which deals with introduction to SQL programming techniques. The sections in chapter 10 include database programming techniques and issues, embedding SQL, dynamic SQL, and SQLJ, database programming with function calls, SQL CLI, JDBC, database stored procedures, and SQL PSM, and then comparing the three approaches. Moving on to the introduction to SQL programming techniques. Database applications, you typically have this concept of a host language that is something like Java, C++, C#, COBOL, or some other programming language. And then you have a data sublanguage, which is SQL, which is used to interact with the data itself. SQL standards are continually evolving, and database management system vendors may have some variation from the standard, and they do have much variation from the standard. Almost no one implements the true standard. There are several ways that you interact with SQL. One of them is through an interactive interface. This is where you type SQL commands directly into a monitor or some sort of session and you get back results. The other way is to execute a list of commands in a file by running some sort of a file through something that interprets it. And the third way here is to use an application program or database application. Typically, it's used as canned transactions by the end users to access a database, may have a web interface. The approaches to database programming. One is to use an embedding sort of approach where database commands are embedded into a general purpose programming language. Database statements are identified by a special prefix. Precompilers or preprocessors scans the source code for the program, looking for those codes and turning them essentially into instructions that are able to be executed on the database system. This is called embedded SQL. Not really done very much anymore. It was for a while. It has some problems. Another approach is to use a library of database functions. The library of functions available in host programming language, typically done through some sort of an API. Design a brand new language, a database programming language designed from scratch. This is some sort of a domain-specific language. The first two approaches are more common. Generally speaking, there's another approach that's not necessarily listed as this, which is to abstract out all database calls and expose them via a web service, similar to an API sort of approach, but in a cross-platform world. The impedance mismatch is a common problem that deals with database languages and programming languages. It's a difference between database models and the programming language. A binding for each host programming language may be created or used. It specifies for each attribute types the compatible programming language types and essentially maps between the two. A cursor or iteration variables is a way of looping over a set of tuples in a query result. The impedance mismatch is a very big problem. There have been numerous ways to try to address it, including things like object relational mapping and other constructs to essentially solve the problem. The summation of that problem is that the objects that need to exist inside of a program when it's executing is not the same as the constructs that need to exist inside of a database when they're being persisted. When we're doing interactions with a database programming, there are some typical patterns we follow. The first is to typically open a connection to the database. The second is to interact with the database by submitting queries, updates, or something else to the database. And then oftentimes we terminate or close the database connection. There are variations on that theme, though. Sometimes you have what's called a connection pool, where you keep open a set of connections that are used by multiple processes, especially in the case of like a web server, where you want something that you don't want to have to pay the cost of reestablishing and closing that connection every time. So sometimes you'll keep a connection open for a certain amount of time, as long as and have multiple processes utilizing it, not just a single process. So when we talk about embedded SQL, dynamic SQL, and SQLJ, embedded SQL is typically whenever you're dealing with something like a C language. So you're sticking SQL inside of the C language with some special tags that essentially convert it into something that can connect to a database server. SQLJ is something similar for the Java language, and programming languages are sometimes called a host language. That's the host language in which the embedded code is running. When we're retrieving single tuples with embedded SQL, oftentimes you do something like an exec SQL, although there are some challenges with that approach, such as things like essentially buffer overflows and so on. So we oftentimes will utilize a stored procedure for our mechanism of retrieving or executing SQL rather than just allowing SQL to be included. There's typically a prefix. A preprocessing separates the embedded SQL statements from the host language. It's typically terminated by some sort of a matching int exec or by potentially a semicolon. Sometimes we'll utilize shared variables. These are variables that are used both inside of C programs and inside of SQL statements. Sometimes there's a prefix of a colon to the SQL statement. This is an example of a C program using embedded variables or using programming variables used in an embedded SQL example, E1 and E2. This is an example of the steps that typically go through where we connect to a certain server as a connection. You do some form of authorization using a username and password, and then you set the connection's name and then potentially disconnect the connection at a later point. SQL code and SQL state communication variables used by database management systems to communicate exceptions on error conditions. SQL code variables, 0 typically means things went well. Something that is greater, say, than 100, maybe something is there's no more data. Usually negatives are reserved for errors, although this is going to depend upon each individual potential SQL implementation. SQL state is a string of 5 characters. In this particular case, 0 would indicate no errors or exceptions. These are a way of looking up what happened and why it didn't go well. Typically, this approach is kind of a bit of a legacy because the error messages should be reasonably self-describing. Here's an example of a program, a segment that is using some embedded code. You can see it's fairly readable. You have an exec SQL with a semicolon terminating the statement, and then the approach at the very end to prompt that there's to get more or not. Frankly, nobody does it this way, not in a very long time. It is something that I would view as being more historical. Lots of reasons to really not be doing this. So, retrieving multiple tuples with embedded SQL using cursors. Cursors are a way of essentially iterating across a collection that is a result of a query. You open a cursor, you fetch commands, and then you close the cursor at the end. Cursors are also something that aren't necessarily all that advisable because of performance reasons. Cursors typically equate to making the database server maintain state. We try to keep database servers stateless if at all possible. So here's an example of using cursors inside of an embedded SQL program inside of what looks like a C variant. Retrieving multiple tuples with embedded SQL using cursors for update of list the names of any attribute that will be updated by the program, fetch, origination, orientation, add values, next, prior, first, last, absolute, I, and relative I. And this is basically a way of declaring a cursor. Specifying queries at runtime using dynamic SQL. Dynamic SQL is a way of executing what's a query that's essentially produced at runtime. It's through some form of typically string concatenation. They allow for things like dynamic querying and dynamic updating. Here's an example of a dynamic query basically being created by preparing it and then selecting it. Again, not necessarily something that's used all that often any longer for lots of reasons, one of which is being performance can be quite bad. The second is being potential security vulnerabilities. Another approach is to use embedded SQL commands inside of Java, standard adoption by several vendors for embedding SQL in Java, import several class libraries, set a default context, uses an exception for error handling. SQL exception is used to return exception conditions. Figure 10.5 shows the classes that are being used and an approach of using it at runtime. Figure 10.6 is a Java program. Variables used in an SQLJ example, J1 and J2. This is another example of using a Java program segment with JSQL. And you basically can see the commingling of select statements with Java code. Again, almost everything that I've ever seen using Java accessing a database is going through JDBC. This is kind of an interesting side note, typically not something that's done. Retrieving multiple tuples in SQL using iterators. An iterator is an object associated with a collection or set of multiple sets of records in a query result. You typically have a named iterator associated with a query result, and a positional iterator lists only attribute types in query results. Figure 10.8 is an example of a program that is using a named iterator to print out the employees of a particular department. Figure 10.9 is an example of using a positional iterator to present employee information in a particular department, so position versus the previous example. Database programming with function calls, SQL, CLI, and JDBC. Use of function calls, dynamic approach for database programming, a library of functions, also known as an API, used to access a database, SQL call level interfaces, CLI, part of the SQL standard. SQL using C as the host language, you typically have an environment record that you track one or more database connections. You set an environable information. You connect a connection record keeps track of information needed for a particular database connection, and a statement record keep tracks of information needed for one SQL statement. Description record keeps track of information about tuples and parameters, and handles to the record. A C pointer to variable makes record access to the program. This is an example of using a CLI C program. Again, not something that's done all that often. SQL function calls for Java programming. JDBC, a Java function library. A single Java program can connect to several different databases called a data source accessed by Java programs. You use something like class.forName of Oracle JDBC driver to make sure it exists. It loads the driver explicitly. You connect, you have a connection object, you have a statement object which contains two classes, prepared statement and callable statement. Question mark is used to pass in parameters. This isn't just JDBC, other sort of approaches such as ODBC and ADO and other mechanisms in general utilize a question mark as a placeholder for parameters which are replaced at runtime. The advantage you have with this approach is that it minimizes your risk of something like injection attacks by making it such that the syntax of the parameter is such that it limits you from trying to do some sort of overflow approach. Then you'll get back a result set which contains the results of the object or something that allows you to page through those results. This is a more common sort of scenario that you're likely to see. It is utilized quite a bit using some sort of an Oracle JDBC driver. In this case, they're connecting to an Oracle database. You can tell because of the driver they're using. JDBC drivers exist for almost every database out there. And this isn't necessarily fantastic because you can see that it's doing a statement preparation, but it is an approach that is valid. A Java program that's using JDBC query with a collection of tuples as its results. Generally speaking, there's some form of pagination that goes on with that as well. Stored procedures are another approach to do programmatic extension. This is actually pretty popular and common as well, much more so than some of the previous things we've talked about. And generally speaking, that is kind of the way that you see it done most of the time, including the storage of those stored procedures inside of a database and so on, or inside of a version control repository and so on. Persistent stored modules, not terribly common from what I've seen. Whenever we declare a stored procedure, you use something similar to this: create procedure, procedure name, parameters. Sometimes there's some additional stuff in there, and you can have it to where it does have a return type or not. Each parameter has a particular type, the particular types, and also may have default values. You may have in, out, or in, out, and you call them usually using the call procedure approach. This is probably your most common way of doing programming against a database. So this is the one to pay attention to. SQL, PSM, extending SQL, specifying persistent stored modules, conditional branching. Most SQL implementations have some form of conditional branching inside of the code, and also they typically have some form of iteration, even though it may not necessarily be a great idea. And that's where this looping is: while, condition, do, and then looping, and then end while. Sometimes you have begin and end blocks inside of those loops as well. Repeats and fors. This is not too uncommon, but it oftentimes goes against the kind of set-based orientation of most database systems. So something to be done with caution. Declaring a function in SQL, PSM, create function, returns, and so on. This sort of thing you see some, but not as often as you do stored procedures, though sometimes these are handy for essentially either this form of a function or adding additional functionality by including some external library, sometimes written in low-level programming languages. When you compare the three approaches, embedded SQL approach, the query text checks for syntax and validation against the database schema at compile time. For complex applications where queries have to be generated at runtime, function call approach is more suitable. Library for function call approach, a library function call approach, more flexible, more complex programming, no syntax checking done at compile time, though you can do automated unit tests to do the equivalent during development phases. Database programming language approach does not suffer from the impedance mismatch problem. Programmers must learn a new language, maybe. In summary, the techniques for database programming, we talked about embedded SQL, SQLJ, function call libraries, SQL CLI standards, JDBC, class libraries, stored procedures, and SQL PSM. As always, if you have any questions, do let me know. That's what I'm here for. Stay safe, and we'll talk again next week.